Last lecture we finished with the model of the PN junction, where we discussed that the PN junction has a exponential characteristics, and along with that, it has two capacitances in the forward bias, the depletion capacitance and the diffusion capacitance here. So today we are going to look at application of these models and the fact that we need simpler model, which we've discussed earlier, in order to analyze circuits. So this is stuff that you've already seen, so I'll just refresh your memories here. Okay, so this is a problem that we had taken up earlier. So we have a circuit here, very simple circuit, voltage source, resistor, and a diode here. And if we have to solve this particular circuit, as I said, analysis of circuit is nothing but transformation of a circuit into equations and then solving them. And so the equations come from here. They come from the Kirchhoff's voltage law here, the Vs equal to IR plus the diode drop here, which is V0. And the other equation that comes, because we are talking only DC here, the other equation that comes is the diode equation I equal to Is, exponent V0 by NVT minus 1 here. So we have to solve these two equations together in order to find out what V0 is. So you're all seeing that, for example, I can take V0 from here and write it in terms of I and substitute back in one equation and therefore get one single equation here. And the trouble, as I said, with this equation is it's nonlinear. So a little bit more involved. The solution is a little bit more difficult. So there are two ways in which we handle nonlinear equations. One of them is we use an iterative method. So I've written down the two equations together. And the iterative method is, for example, you assume a value of V0. We don't know what V0 is. You assume a value of V0 here. So let's say I don't know the diode drop, so I assume 0.6. And next thing is we use this equation to calculate the current. Okay, so I get a value of I. And then once I get a value of I from this equation 1 here, then I take this I, substitute it back here, and I get a new guess for V0. I get a new guess for V0, and then I go back here, and I keep on iterating till I obtain convergence, till I find that my current is no longer changing much, that delta I by I is less than a certain threshold here. And then I say I attain my solution here. Okay, so just to illustrate, I have this equation, diode equation here. So Is is given, ideality factor N is 1 here, and we are also given the thermal voltage here. So this is a procedure. So say I assume 0.5, I get a current here, I get 0.711, I go back to 0.711 here, recalculate the current, 0.707 here, put back 0.707, and at least to the third decimal place is no longer changing. Okay, and therefore I have my solution here, 0.707. So that's one way of solving nonlinear equations. Okay, you can use an iterative method. The other way of doing it is, well, you may be wondering, will I obtain convergence if I go to some very different value here? I'll just quickly show you. You start with 1, and you end up with 1 also the right answer. Okay. All right. So the other method is, if you don't want to do iterative method, the other one is the method of load line, which is very common in diode circuits and common in BJT and MOSFET amplifiers. It used to be more popular earlier when we didn't have access to the computers. Okay, so let me just illustrate here. So again, the same circuit is here, and the equations are Vs equal to IR plus V0 and the diode equation. So these are the two equations that we have to solve. So what we do here is this equation that you see here is I in terms of V0. So the first equation also, we write it in I in terms of V0. So now we have two equations, both of them in terms of V0. And you know that if I plot them out, the intersection of the two will give me the solution here. So that's what one does here. So one writes it in terms of I versus V0 here. So the first equation is here. And the method gets its name from this equation here. This is the load line here. If I call this the load resistor here, R, and so this is the load line here. Okay, so that the method gets its name from this particular line here. And the second equation is a diode equation. So you plot this out, and the solution is the intersection here. Okay, so that's one method. Now the diode graph remains the same, and depending on different values of R, I'll get different. What will change if I change the value of R? This point is Vs. If I change the value of R, this point will come down, and the slope will also change. So I can draw different lines here, and they will give me different solutions. Okay. So that's the other method. As I'm illustrating here, you can use it with diode, you can use it with transistors to find out what the solution is. Okay, this is illustrating the same thing here. All right, we've seen that for hand analysis of circuits and for carrying out initial design, we need simpler model here. And this simplest model for a diode is here, V gamma, where you approximate the diode by a cut-in voltage here or a turn-on voltage here. In the forward bias, reverse bias, you assume it to be open. And so one of the models, as we commonly take, we approximate it by 0.7 volts. This is true for some of the diodes. So I've shown here again a similar circuit, and I have a diode model here. And what I'm trying to assess is how good is my 0.7 volt model here for different values of R. Okay, so I've taken a fairly wide range of R from 10 ohms to 1 mega ohm, right? 10 ohms to 1 mega ohm here. And so what I'm going to do is change the value of R, calculate current using this particular model. And if I assume 0.7 volt, the current simply becomes 1 by R. 1.7 minus 0.7, so it gives me 1 volt, 1 by R. So current is very simple, and I vary R and I get a current here. So that's one way of calculating current. The other way would be to actually use the exponential model and calculate current directly without making approximation. And then let's see the error here. So that's what happens here. So my model, the simple model assumes 0.7. The actual diode drop is changing in this particular manner here. Okay, the actual diode drop. So obviously, when the resistor is small, I have more current. And if I have more current, the drop across the diode is also larger. As I go to large values of resistor, the current is smaller and the diode drop is also smaller here. So you can see the changes that are occurring in the diode drop here, starting from almost like 0.8 going down to about 0.5 here. And we are approximating it by 0.7 here. So this is what is happening here. So the diode drop is of course changing depending on, so at one point, for example, if I go and look at 1K, it's pretty good. The approximation is pretty good. 1K, the current is 1 milliampere, and for our diode, the voltage is very close to 0.7. But if you're going to very high values of resistors, which means very low current, then the errors will increase. And similarly, if you go to very high currents, the error will also increase here on that side also. Okay. This shows the error in the current that I get. All right. Now, this was for one diode here. Okay, the diode parameters are given. 2 times 10 to the minus 15 is the saturation current and all of that. Let me take another diode. This is a diode 1N4148. You can find it in the lab. IS for this is 5.9 into 10 to the minus 9 here. Note, saturation currents are very different. N for this case is 1.91. Ideality factor is 1.9. It's not 1. All right, so depending on the diode, you may find different values of N and different values of IS will be there. So if I do the same thing here, this is what I find. Same circuit. If I apply, again I'm assuming 0.7 model here. Actual analysis gives me this kind of a behavior here. Now in this case, note that at around 1 mega ohm, the current is small and the diode drop is maybe 0.25 or so. The diode drop is around 0.25. So very small diode drop here. Okay. So diode drops, as I told right in the beginning of our discussion on PN junction, can be very, very different from 0.7 volt here. It all depends on the diode. Okay. Now, why is the diode drop so small here? What is the difference between this diode and the other diode? Go and look at this current here, saturation current. Saturation current is 2 femtoamperes. 2 femtoamperes, right? So if a saturation current is 2 femtoamperes, and for a certain current I to flow in the circuit, obviously you'll require a larger voltage. Now go back and look at the next diode here. The next diode is nanoamperes. So this was nanoamperes of current and the other one was femtoamperes of current. And that's why the difference is there. That in this case, for same current to flow, I have to use only 0.25 volts. And the other case, I have to use 0.5 volt here, close to 0.5 volt here. Okay, so the differences come about because of the different values of the saturation currents that you see here. And some differences also come about. Ideality factor N is 1 here, and in the other case, N was close to 2. Now, how come the two diodes have different values of saturation current? Well, you know, these diodes are PN junction diodes. So one of the differences that come about is I have different doping. The doping in semiconductors can vary from, let's say, 10 to the power 13 or 10 to the power 14 all the way to 10 to the power 19. So I can change doping over a very wide range. So that's one source of variation in IS. The other source is the diodes that I can make them of different areas. I can make a diode which has a very small cross-sectional area, and therefore it, IS for it becomes small. And for another diode, I can make it of a larger area, IS becomes large. So depending on the area of the diode also, I get different amounts of saturation current here. So all that I was trying to illustrate is that my diodes can differ drastically in terms of the saturation current that you see here. And therefore, in this case, you may think that approximation of 0.7 is not too bad. It's okay. While in the other case, the 0.7 volt approximation becomes pretty poor, especially as you go to larger or smaller currents. Okay. So you have to watch out for, while you're using 0.7, you have to watch out for the fact whether the model is correct or not. And there is a very quick check that you can do. Whatever circuit you're solving, and let's say you've assumed 0.7 volt, fine, you get a value of current, right? For that value of current, just go and calculate this drop here. Use this equation. Where is that equation? Here. For whatever value of current, you can use this equation, right? So you solve a circuit with a 0.7 volt model, you get a certain value of current, let's say 1 microamperes or 1 milliamperes or 10 milliamperes here. Just do a quick check, take that current, you know the diode, and calculate what the value of the voltage is. If it's okay, if it's nearby 0.7, if it is 0.65 or 0.55, you're okay. You don't care too much. But if you find it's 0.2 or 0.3, right? So then you can do a correction and assume that your diode can be approximated not by 0.7, but by a 0.3. And then it would be okay. All right. So be on guard that 0.7 volt model may not always be applicable. And then you can easily check whether it holds true or not. Now, having said that, the 0.7 volt model may or may not be valid. From henceforth, throughout this particular course, when we see a diode, we'll replace it by 0.7 volt. Okay. Having said that, so reminding you that it may not be true, but for various analysis, we want to quickly analyze and see what is happening, and we'll use 0.7, okay, for analysis. All right. Coming back, as I've said earlier, and we discussed in the homework assignment also, the error in the diode model that we have, it translates into an error in current. So many times you're not really interested in how accurate the diode model is, because you're using the diode model to calculate some current or power or whatever. You're interested in how accurate the current calculation is, let's say, or how accurate the power calculation is. So obviously, if you look at it here, in this case, if my interest is in current, not so much in the voltage here, then I is V minus VD by R, del I. Now, what do I mean by del I now? I'm saying I'm using an approximate model, so there is an error in VD. Okay, I'm using a 0.7 volt model, let's say there's an error in VD. So because of an error in VD, diode drop, I'll have an error in I. So del I will be equal to minus del VD by R. And of course, I'm interested in percentage error. So del I by I will give me del VD by V minus VD here. And so therefore, it tells you that the percentage error in current actually depends on how close this should be actually VS. This should be VS. So how close my VS is to VD. That's critical here. I can have the same, for example, I can have 1K here. And if I apply 1 volt here, I have 1K and I have 1 volt here, and this is 0.7. So V minus VD is 0.3. So I'll have a certain amount of error. On the other hand, if I put here 100 volts, then obviously you can see that V minus VD is going to be very large and the error is going to be small here. So the error in the quantity of your interest has to be separately calculated. You have to look at what is the error in my diode model and how does it translate into the current here. Okay. And suppose so if we are doing this problem here, 1.7 and here. Suppose I replace this battery by 0.7 volt. What will you do then? What will you do? If this voltage were 0.7, all right, what will be the current? Obviously 0.7 volt model completely fails here, because if I put 0.7 here, this is 0.7 and the diode drop is also 0.7, and you'll say current is 0. Current is obviously not 0. Okay, so you have to assume what? Maybe you have to assume, let's say the diode drop is 0.6 or something, or 0.5. Right? So suppose I assume that diode drop is 0.5. It's arbitrary. 0.7 minus 0.5 divided by R will give me a current. And once I know a current, from this equation I can recalculate a better diode drop. And the better diode drop may turn out to be 0.6 or 0.5 or whatever. And with that you do the calculation. Okay? So that sort of illustrates if I had a 0.7 here, obviously I can't live with a 0.7 drop diode model here. So as we discussed in the homework assignment also, a better diode model is the fact we know that the diode drop is changing with current. So a better model is that we approximate it by a voltage, a battery here, cut-in voltage V gamma. In addition to that, we add a resistor R. Now we know that as the current changes, the diode drop will also change here. So that's a better model. Now we have a diode drop which is changing with current, which actually reflects the reality here. And in reverse bias, we continue to use open circuit here. So this is what we mean by this particular model here. When you see something like this is my actual diode characteristics, and what we are saying is we are approximating it by a piecewise linear model here. Okay, so we are saying till this V gamma, we are saying that the voltage across the diode is till beyond V gamma is a straight line here. Okay, so that's our approximation. The slope here of this particular line, it gives us the series resistance in the diode here. Okay, so that's the approximation that you are making here. It's an exponential characteristics, and you're approximating it by one piece of line here and another piece of line here, and you're approximating by these two line segments here. And again, it all depends on the approximation that you're making, depends on the range of current that you take here. Okay, so let me illustrate again for you. Let's say, look at this, it's the same diode model that I have. Okay, and now look at the range of current that I have. The range of current is, it's around 20 milliamperes, 30 milliamperes. That's the range of current. Okay, so if I'm talking about currents in the range of 10 to 40 or 50 milliampere, then what I'll do is, again, I'll draw a line here up till here and approximate it. Okay, so this is what I'm doing, approximating it. And if I do that, then V gamma for me turns out to be 0.75, and the slope gives me the value of R, which turns out to be 1.4 ohm. Okay, and my average current over which this model is valid is around, let's say, 25 milliamperes or so. So that's my approximation. Note a very important point, the scale on which I'm working. On this scale, this is a good approximation. Seems like a good approximation from current from about, let's say, 10 milliamperes to up to maybe 40, 50 milliamperes here. So over this current range, I'm going to approximate my diode by a cut-in voltage of 0.75 and a resistor of 1.4 ohms. Now you change the scale, everything changes here. Now I have a scale of current here, so the range is 0.25 milliamperes here. So earlier I had a range of, average current was about 25 milliamperes here. Now it is 0.25 milliamperes here. So I do the same thing here. I approximate it by two line segments here. Now it comes out to be 0.63 and the slope comes out to be 150 ohm. Okay, so it all depends on the range of current that you're interested in. If this is the range of current, then this is the appropriate diode model here. 0.63 volt is the cut-in voltage and the series resistance is 150 ohm. If you had a range of this one here, then of course 0.75 here and a series resistance of 1.4 ohms. So the model, as I made a general statement, model is a representation for a purpose. If your purpose is to approximate the characteristics over this current range, you have this model here. If your purpose is to approximate the characteristics over this range, then you have a different model, 0.63 and 150 ohm. Okay. So the manufacturer will not give you a model. The manufacturer will give you what? The manufacturer will give you IS and N and all of that. Now, out of that characteristics, you have to build your own model. Depending on the range of current that you are interested in, you have to approximate it by a suitable value here and a suitable value. Okay, so that's your task. As an analog circuit designer, you may have to do this. What value of V gamma and what value of RF is suitable for your circuit here. Okay. Well, of course, there are even simpler models here. We've talked about it. Even simpler model is short and an open here. So these are the, I put this picture earlier also. These are the different models that you see here. Models increasing in simplicity, model increasing in accuracy here. And these are things that you know here. Well, as I said, sometimes even the simplest model that you see here doesn't give you very bad results here. A diode in forward bias is a short circuit and a diode in reverse bias is an open circuit. If I use it with a circuit like this particular model gives me 10 milliamperes. The second model, constant diode model, constant voltage model gives me 9.3. The second one, the third model, which I approximated by a resistor, gives me 9.208. And the last one, more accurate, gives me 9.24. So these are the values that it gives. And even, you can see here, even the simplest model is not too bad. I have error which is less than 10% here. 10 milliamperes here, 9.24. Many times I'm quite happy with that kind of analysis here, with that kind of error. So even this model is okay. So again, it all depends on your application. Okay. And if I had put here 100 volt, this model would have been even more accurate. Okay. So there's no point. So what it is illustrating here is there's no point in deploying this particular model. If you just want to quickly estimate what is the current flowing in the circuit, what is the point in doing a iterative analysis or a load line to figure out 9.24? You're quite happy with the fact that the current is around 10 milliamperes or even 9.3 milliamperes, and you can go on and proceed with whatever your task is in terms of design. Okay, so there's no need for doing it. A different, of course, this one will, of course, will tell you the necessity of a more accurate model here. So if when I went from 10 volt to 1 volt here, now you can see the error. This predicts 1 milliampere, the 0.3 here, 0.297 and 0.329. Of course, now this is grossly inadequate. It predicts totally wrong values here. Okay. All right. Let's come back to now a small signal model. Small signal model, we know, is always evaluated at a bias point. My diode is already biased at some DC value. And then what we do, we are talking about what happens when I change the diode voltage by a small amount. There will be a change in current by a small amount, and we are looking at the relationship between small current and small voltage here, right? So that's the relationship that we are looking for. And this is a general method that we use. We change VD by small VD here, ID, small ID here, and then we write it out, this relationship. And then we use a small signal model because we are using a linear model here. So we approximate it by a linear equation that we expand it, and we keep only the linear term. We keep only the linear term, ignore all the second order terms and third order term here, and that allows us. So, and that we can do only if my VD by NVT is much less than 1. If I do that, then all these terms go away here. So if I make that approximation, that the small signal diode voltage divided by thermal voltage has to be much, much less than 1. So that's a key approximation. The small signal diode voltage has to be much smaller than the thermal voltage here. Okay, most of the time we'll take n equal to 1. So it basically boils down to the small signal diode voltage much smaller than 26 millivolt. Okay, and as long as this is true, then my diode can be approximated by a resistor. I keep only the first term, and the relationship between ID and VD is a resistor here, and with a value equal to NVT by, this should be a capital ID, NVT by ID here. So this is not small ID, capital ID here. So that's my small signal model of a diode here. Now, so that's and you can use it whenever you have a small signal in your circuit, and this approximation is valid. And as I've illustrated in the homework assignment, it only tells that the diode drop or the voltage across the diode has to be much smaller than VT. It doesn't refer to that the applied voltage is much less than VT. No, it's only this condition that you have to ensure. How small, again, as I've explained, how small really depends on how accurate an analysis you want to do. If you want a very accurate analysis, maybe you want to keep VD to 1 millivolt. If you are happy with maybe 10% error or so, you can keep it 5 millivolt or 6 millivolt of that kind. Okay. Another thing that I want to emphasize here, I wrote here DC or low frequency model, which means, now remember this voltage that you see here, the small diode voltage or the small diode current. That small current or a voltage can be DC. It can be DC. It can be a sinusoidal voltage. It can be a triangular wave. It can be a square wave. It can be anything. All that we are saying is it's a small voltage. It can be anything. All right. But the model that I have derived, I'm saying it is either a DC or it's low frequency sinusoid. Low frequency. Why? Because when I go to high frequency, my diode is not simply a exponential current. Along with that, what do I have? I have capacitors. Okay, so when I go to high frequency, then what will happen is the diode will be approximated by this resistor, and in parallel to it, what will I have? The capacitors. Because I remember we discussed that a capacitor remains a capacitor when you build this incremental model or a small signal model. It's a linear. So all that you need to do is, if you go to high frequency, in parallel to it, add a depletion capacitance and a diffusion capacitance. And that will complete your high frequency model of the diode. And this is simply a low frequency model of the diode. All right. Okay, one last thing before we stop our discussion related to diode, which is the temperature dependence. If I look at my diode current, ID equal to IS exponent VD by VT minus 1 here, where is the temperature dependence coming from? Obviously VT. And that's a common mistake that everybody makes. Okay, because IS is also a temperature dependent term. If you just focus on VT, because VT is visible to everybody, if you focus on VT, what it tells us is that if I keep my diode, let's say if I apply a constant voltage to the diode, then as I increase temperature, VT will increase and current should decrease. But that's opposite to what really happens. As you increase the temperature, yes, this term goes down, but what happens is this term goes up. IS goes up. Saturation current that you see here in the diode, it changes very rapidly with voltage. Very rapidly with voltage. So this term is decreasing with voltage and this term is increasing with voltage. And it turns out that this term is dominant as compared to this one. Okay, so let me show it to you. So this should be a small q here. This term, look at it. IS is proportional to intrinsic carrier concentration. It goes as e to the power minus Eg by kT. What is Eg? Eg is the energy gap of silicon. So the first term, Is, is going as e to the power minus Eg by kT. The second term is going as exponent. KT is what? KT by Q is actually, I can write this as KT by Q also. So this is also thermal voltage. Okay. So the first term is going as e to the power minus Eg by Vt, if you would like. And the second term is going e to the power Vd by Vt. Now, Eg is how much? 1.12. Band gap of silicon is 1.12. And what is the typical diode voltage? 0.7. So now you can obviously see this is minus 1.12 and this is e to the power 0.7 by Vt. And therefore, if I multiply it together, let's say if I'm looking at in the forward bias, minus 1 is not there, the whole term will be a negative term. A negative term means the current is going to increase. So as I increase my temperature, my current in the diode will increase with temperature. Okay, so that's the characteristics of PN junction diode here. All right. Another way of saying the same thing. So right now what I'm saying is if you keep Vd constant, then the current increases. On the other hand, suppose I said if you keep current constant, what will happen to Vd? For the same current, if you increase the temperature, what will happen to Vd? Vd will obviously drop. Okay, but how much does it drop? Well, there's a rule of thumb here. So the rule of thumb is that for silicon diodes, Vd decreases at a rate of around minus 2 millivolt per degree Celsius. It can be minus 1.8. It can vary. Of course, it's a simple approximate number. So that's something to keep in mind here. What is this saying? If you bias your diode at a constant current and you change the temperature, the drop across the diode is going to decrease at this rate. All right. So let's say you are analyzing your circuit at room temperature. And at room temperature, the approximation 0.7 volt is, let's say, good. Okay, so you're using 0.7 volt and you're analyzing the circuit here. Now, as you raise the temperature, so you're assuming 0.7 at 27 degrees Celsius. The same circuit, if you analyze at 100 degrees Celsius, what diode drop should you take? 0.7 minus 2 millivolt multiplied by 100 minus 27, whatever is the extra temperature here, right? So 0.7 minus 2 millivolt multiplied by 100 minus 27 gives us 0.55 volt. So this is also emphasizing that 0.7 volt drop, even if it's a good approximation at room temperature, it will not be a good approximation at 100 degrees Celsius. At 100 degrees Celsius, if 0.7 is a good drop at temperature at 27 degrees, then 0.55 is a good approximation at 100 degrees Celsius. Okay, so that's another very important point that you have to keep in mind. The diode characteristics is highly temperature dependent, and the diode drop decreases at this rate here. Now, this is only for silicon diode. If you have a different diode, the behavior will be different here. Okay, the behavior will change. This number will change. Okay. Now, many times this temperature dependence is a nuisance. The fact that my, if I make a circuit, I want my circuit characteristics to be independent of temperature. Let's say if I'm making an amplifier, I want its gain to be 100, whether it's at room temperature or at 100 degrees Celsius. Whether it's winter or summer, I want the characteristics to be independent of temperature. And then these diode drops and all these drops here, the fact that they're temperature dependent becomes a nuisance. But of course, from another perspective, it can be, what can you do with it? Well, you can make a temperature sensor, right? And many temperature sensors in the market actually use the diode as a temperature sensor. And let's see. Yeah. So let me just illustrate how you could build a temperature sensor. Okay. So let's take a diode here, PN junction diode. And suppose I have a current source. I build a current source, I pass through it. Okay. So I'll get a voltage V01. What will be the drop here? VD1 will be equal to VT ln I1 by IS plus 1. Can I use this as a temperature sensor? Yes or no? Why not? Well, I pass a constant current. So I have a circuit. I build a circuit as a constant current source and I pass it through my diode. And therefore, there will be a voltage here. And the voltage will vary with temperature. What is the problem? IS is also dependent on temperature. So, well, that's even better. Why is that a problem? All I care is that this voltage here should be temperature dependent. What is it? Yeah, sure. But, as I said, if I bias my diode at a constant current, the voltage across the diode will change at 2 millivolts per degree Celsius, right? So it should change. Why am I not happy with it? You're on the right track. Why am I not happy with this expression? Huh? Nonlinearity. Why is nonlinearity bothering you? Why is it bothering you? The fact that so what you're saying is my diode drop is not directly proportional to temperature. There is a temperature part here also. Why is it bothering you? Let it be. Where is it difficulty? Calibration. So what you're saying is, okay, if I measure the diode drop, if I'm using it as a temperature sensor, if I'm measuring the voltage here, how do I infer the temperature? All right. How will you do that?
The difference between two temperatures will become dependent upon where we are measuring it. It's not linear. So it would be difficult to calibrate it.
So what if I do the following? I build the circuit, right? And I have a oven, and in that oven I can change the temperature from, let's say, 0 degree to 100 degrees Celsius. So what I do is I change the temperature, I measure all of these voltages here, I keep a table, right? And then I go ahead and put that out in the sun, and whatever is the voltage, I go and read the table and tell you what the temperature is. Why it seems difficult? Earlier it was difficult, right? Earlier I could not automate that process. You could make a calibration chart, then measure the voltage, and then look against the chart and say, well, this is the temperature. But that's very inconvenient, all of you are saying. But now it's very easy, right? All I can do is once I measure these characteristics, I don't know whether you're familiar or not, I can take a microcontroller, and in the memory of the microcontroller, I can store all the table, and then interface this particular circuit to the microcontroller, who will read this particular voltage, and then check against the table, and match, and then tell you what the temperature is. So I can very nicely automate it. No problem. It used to be a lot of problem earlier, as I said, because you know microcontrollers and all of that were not that common. But again, it's also a more expensive solution. To use a microcontroller is a digital circuit. I have to use an analog to digital converter. I have a memory. It's a slightly more complicated solution, but you can easily do it. But what would be a simpler way of doing it? I want my voltage to be proportional only to temperature and not have this nonlinearity. What do I do? How do I get rid of this? Huh? Another diode. Okay, then? There's another problem in this particular circuit that I want to point out is, one is of course nonlinearity that you see here. The other one is, suppose you take build a circuit like this and you calibrate it. And you know that every time you measure, let's say 0.65, the temperature is say 20 degrees Celsius. Now the trouble is that different diodes that let's say a manufacturer is making diodes and is making thousands of diodes. There's a lot of variation in IS. IS varies a lot. What does it mean now? Every temperature sensor that I build, I have to calibrate. It's not that once I build a calibration chart, it's valid for all the temperature sensors. No, because IS changes a lot. You know, when a manufacturer is using identical process for making these diodes, there's a lot of variation from one diode to the other diode, especially in IS. IS varies a lot, which means that every circuit will have to be calibrated separately. Okay, and that makes it complicated. That makes it more expensive, the whole process here. So the idea is we want to get rid of IS from here. We don't want IS. And we want to preserve VT. So what do? Somebody said use another diode. Okay, all right, right track. So I use I1 and I build VD1 here. I use another current I2 and same circuit, same diode here. We put VD2 here, and then we get VD2 is VT ln I2 by IS plus 1. And then what do? All of you are familiar, maybe take an op amp. I'm not showing the whole thing. Make a difference amplifier, connect it up here, and you get a V0, and V0 will be C K by Q ln I2 by I1 into T. Two things have happened. It's become linear. V0 has become linear with temperature. So all I need to know is this constant. If I know this constant, then immediately when I read the voltage here, I know the temperature here. So it becomes much simpler. Now the trouble is, this diode and this diode they may have, whatever I assume, same IS. They may have different IS. So now what do you do? How do you take care of the fact that this IS, so I've assumed that IS1 and IS2 are the same. They may not be the same. So one way of tackling this is that what you do is you build the whole thing on one silicon IC. You make an IC out of it. Now, how does that solve this particular problem? Now, what happens is, if you make a diode today, let's say you have a line for making diodes. You make a diode today, you'll have some value of IS. You make a diode tomorrow, we'll have some other value of IS because of some changes that are occurring. But if you have a same silicon IC, and on the same silicon IC, if you make a diode D1 and D2 as neighbors right next to each other, then what happens is the IS of the two diodes will be very close to each other. See, absolute value of IS I may not be able to control. From one wafer to the next wafer, or from today to tomorrow or month after, I may not be able to control. But if I'm making the two diodes at the same time on the same wafer, then the IS of the two diodes are likely to be very similar. So one way of doing it is even if you don't want to make the whole circuit on an IC, don't use one diode but make a pair of diodes. So what the manufacturer can do is sell you not single diodes but pair of diodes. And if he sells you a pair of diodes, then what you will find is that pair of diodes will have very similar IS. And then the rest of the circuit you build externally and add that, and that's fine. So that's one way of taking care of. Or now you can integrate the whole thing on an IC also and sell the whole thing as a temperature sensor. That is also possible. But suppose I don't want to use two diodes. Can I work with one diode? Let me throw a challenge to you. So the problem with this circuit is IS1 is different from IS2. One way of saying is I'm going to build a circuit not with two diodes, with one diode itself. Can I do that? With one diode only. And I want to exploit this particular fact, right? That is what makes so the point, I hope you're saying, so I want to use the difference of the two voltages to get this relationship. It's a linear relationship, there's a cancellation involved, and that's beneficial. But at the same time, I don't want to use two diodes. And still I want to do this. Huh? I1 is temperature dependent. That will complicate a little bit more. Yes. So what I'm saying is I want to do this difference, but I don't want to use D2. It's pointing to what I'm saying. So suppose I put a switch here. Suppose I put a switch here, right? And first I drive my diode with I1, right? So I will generate V01. Then I drive my diode, same diode, with I2. Then I will generate V02. And then I apply V01 and V02 to this particular difference amplifier. But then you may say, when I drive with I2, what will happen to V01? It will go away. So what else do I need? Huh? I need a memory. And what's a good memory? Very simple memory. Capacitor. So what you do is, I'm not giving, think about the solution, you can work it out yourself. So what we are saying is, maybe put a switch here, maybe put a switch here. So what you do is, and so the input to the differential amplifiers that you see here, they go from a capacitor. There's a capacitor here and there's a capacitor here. So what you do is, you take this capacitor and first you connect this capacitor to here, first capacitor, and then you connect it to I1. And therefore you store a voltage V01. Next, to this capacitor, you connect this voltage here. You have switches, and then you connect I2, right? And then you have V01 and V02, both derived from the same identical diode, and then therefore you get V0, right? So you get rid of the fact that IS is different from different diodes here. So maybe you can do that. What is the price that you have to pay? Capacitors, switches, and all of that you need to do. One major price that you have to pay is when you build capacitors, you have to store charge, right? So you have to build capacitor of a significant size. If I put a picofarad capacitor, it's not going to work. So I have to build capacitors of a certain size. The trouble will come, I can't build these capacitors on silicon. On silicon, you can only build very low values of capacitors in picofarads. You can't build nanofarads of capacitor. Okay? Which means that the whole circuit, you will find it difficult to integrate on silicon. Those capacitors will have to be external. And when something becomes external, it becomes bulky. It's not, it's not as compact. Okay, so that's the price that you may end up paying for that. So I'm just pointing out the possibilities, and it's very common to use diodes as temperature sensors here. And so we are seeing how one may do that here. Okay, I was thinking of starting bipolar. We don't have enough time. What else can we use a diode for? All of you know that